Good morning, my dear students. My name is Dr. KCH Apparao, working as an associate professor in mechanical department, Institute of Aeronautical Engineering, Hyderabad. So this is our subject heat transfer. Okay, in previous classes we discussed the general heat conduction equation in Cartesian coordinate system. You know that according to the Cartesian coordinate system, we got the conduction equation like this: dou square t by dou x square plus dou square t by dou y square. So del square t by del z square plus q by k is equal to 1 by alpha into dt by or dou t by d small t. You got this formula for the heat conduction in Cartesian coordinate system. You know that alpha is the thermal diffusivity. So dt by d small t, it shows the steady state condition. Okay, so for just like from this one also, so we got the rate of heat transfer in slabs, just like we already derived this formula. Q is equal to Ka into temperature difference, so T1 minus so T2 by L. So if there is more number of slabs, it means for the composite slabs also we derived the formula in previous classes, just like so T1 minus so T2 by so L1 by K1A plus L2 by K2A, so plus L3 by so K3A. So for the for three layers are there. So if there is many number of layers are there, just you can take ln by kn into a. So this is the formula. So in previous classes already we discussed about this one. So also we discussed the just like general heat conduction equation in cylindrical coordinates. In cylindrical coordinates. So that one also we already discussed it in previous classes. So from this formula we got that one. So that is the dou square t by dou r square. So plus 1 by r into dou t by dou r plus 1 by r square into dou square t by dou pi square. So plus, so similarly just like dou square t by dou z square plus so q by k is equal to 1 by alpha into dou t by so dou small t. So this one also already we derived into the previous classes. So it represents just like dou square t by dou r square plus 1 by r dou t by dou r plus 1 by r square into dou square t by dou pi square. So this is the just shows the dou square t by dou x square and dou square t by dou y square. So because you know that in the cylindrical system, so x component is the r cos theta, so cos pi. So y component just like r sin pi. So based upon this one, just we derived this formula. We already solved in the previous classes also. In this class, just like we'll derive the formula for the rate of heat transfer. Rate of heat transfer in cylindrical system. Rate of heat transfer in cylindrical or cylinders. So previous classes we already discussed the rate of heat transfer in slabs. So here just like we will derive the rate of heat transfer in the cylinders. Just like you know the formula. So Q is equal to 2 pi KL into so T1 minus T2 by R0 minus so Ra. So we derive this formula. So as usual, you know that this is the formula already derived in previous classes. So this is the heat conduction equation or general heat conduction equation in cylinders like this one. You know that if you take this is the just like steady state condition. So this will be 0. You know that if it is steady state condition, so dt by d small t will be 0. So then the formula will be like this one. So dou square t by dou r square, dou r square plus 1 by r into dou t by dou r plus 1 by r square into 1 by r square into uh, dou square t by dou pi square. So plus dou square t by dou z square plus q by k is equal to 0 if it is in steady state condition. If you consider heat generation in the small elementary area will be 0. If you consider there is no heat generation, then the formula will be like this one. So this is directly equal to 0. Okay. So it means the total term is equal to 0 means this total term is equal to 0 and those were t by dou z square is equal to also 0. So we can take any one this one. So this is the 0. So like this one. So according to PBTs, you can understand here. So this one is the so according to this one, so this total term is equal to 0 means this one also 0. So this one also 0. So this total term also t. So from which just like this is the radial surfaces. So I am taking this term. This is equal to 0. Okay. So okay, we can rewrite this formula like this one. Just like 1 by r into d by dr into r dt by dr. So if you derive this one, just like derivative this one with respect to r, we will get this one. Okay. So this is the just a final formula. So from this formula, by using this formula, we will get the rate of heat transfer in the cylinders. Okay. So for this one, just like we take one hollow cylinder. So this one is the axis like this one. So inner diameter is equal to Ri and outer diameter is equal to R0. Okay. So inner temperature is equal to Ta, outer temperature is equal to T0. So take small elemental area. So small elemental area. So which is the R is the radius and temperature T is the temperature at that one. So first of all, you have to find out the temperature. So what is T with respect to T and Ti and T0 and Ri and R0. Okay. So for this one, just like we can integral this on both sides. If you apply the integral this one, just we will get the formula like this one. So for this integral is just like we can apply the boundary conditions also here. So boundary condition, there is the two boundary condition, inner surface, outer surface. If the temperature is equal to Ta or R is equal to Ri, temperature is equal to Ti. So that is the boundary conditions. So T is equal to temperature is equal to Ti when R is equal to Ri. So that is the boundary condition one. So similarly, T is equal to T0, R is equal to R0. This is the secondary boundary condition. By using the boundary condition, just like we find the temperature T. Okay. So for this one, just like I am taking that one 1 by R dou by d by dr into R dt by dr is equal to 0. Just like okay, integral both sides, just integral here, integral here. So if you integral this one, just integral derivative will be cancelled. Then we'll get R dt by dr is equal to integral of 0. The constant will take C1. Okay. So similarly, just like we can send this R to right side. So then dt by dr is equal to here dt by dr is equal to C1 by R. So then again integral this one like this one. Integral dt by dr is equal to integral of C1 by R. Okay. So then we will get the general equation. So T is equal to, you know that C1 is the constant, 1 by R, integral of 1 by R is equal to ln R. So plus C2. So this is the general equation in T. Okay. So then we apply the boundary condition. You know the boundary condition, if T is equal to Ti, then R is equal to Ri. If T is equal to T naught, then R is equal to R naught. Apply the first boundary condition. Just these are the boundary conditions. So first of all, apply the first boundary condition. What is that one? So R is equal to Ri. So where T is equal to T. So applying the first boundary condition here, just like you can write like this one. Just I am applying the first boundary condition. If T is equal to Ti, C1 plus Ln, R is equal to Ri plus C2. If T is equal to T naught, outer temperature, C1 into Ln R naught plus C2. Okay. Okay. So from which, just like if you subtract from equation 1 to equation 2, like this minus. So then this is the Ti minus T naught is equal to, so C1, C2 plus C2 minus C2 will be cancelled. Then C1 is the common term, you can take common. Okay. So this is the Ln Ri minus R naught. You know that Ln R naught. So log A minus log B, you know the formula. So you can rewrite like this one, C1 into Ln Ri by R naught. So from which C1 is equal to Ti minus T naught by Ln R naught by Ln Ri by R naught. So this is the C1 value. So like this one, just like again I am showing this one. Listen carefully. So this is the just like, so if you apply the first boundary condition, Ta is equal to C1 Ln Ri C2. Second boundary condition, T naught is equal to C1 Ln R naught plus C2. So when you subtract from the equation 1 to 2, then we will get to Ta minus T naught is equal to C1 into Ln Ri by R naught. So from which we will get the C1. C1 is equal to Ti minus T naught by Ln Ri by R naught. So this is the one more thing, just to remember this one, dt by dr is equal to C1 by R for the solving of Q. Okay, just like you know the conduction equation. Okay. So just according to the Fourier's law, we know the formula, that is Q is equal to minus K into dt by dr with respect to R. Okay. So you know that dt by dr is equal to, according to the previous slide, I already explained that one, dt by dr is equal to C1 by R. So from the previous slide, you can remember that one. Okay. So just like substitute this value C1 by R in this Fourier's law. Okay. So then Q is equal to minus K into C1 by R. You know that. So C1 value, what is the C1 value? According to the previous slide, C1 is equal to Ti minus T naught by Ln Ri by R naught. Okay. So this is the C1 value. Substitute this C1 value in this formula, then we will get this one, just like minus K, area of the just like surfacial area, lateral surface of this area. So this is the, so according to previous slide, already I have given that diagram also. So this is the length. Okay, so this one is the length. Okay, so this is the elemental area we have taken. So that is the R. So area of the small elemental area is equal to so pi dl or 2 pi r into L. So that is the area. So from this one, so Q is equal to minus K C1 by R. C1 value is substituted here. So then, and A value, area of this cylinder, so also substituted here. Then we'll got this, the formula, that is the 2 pi KL. So because this R, this R will be cancelled. Okay. So, and temperature difference, so what is Ti minus T naught. Ti minus T naught. Here minus is there. So we can change the interchange this one. So here the formula is equal to ln Ri by R naught. So if you consider the minus, so we can change like this one. So you know that Li Ri by R naught means Li Ri minus ln R naught. So if you consider this R minus, then this will be like this one, ln R naught minus ln Ri. You know the log A minus B. So log A by B R naught by Ri. So here just like because of this minus ln R naught by Ri we got. So this is the formula. This is the formula for the rate of heat transfer in cylinders. Rate of heat transfer in cylinders. So how to remember this formula? Okay. So now we'll see the rate of heat transfer in composite layers of the cylinders. So different layers, coaxial cylindrical layers. So same axis they have. So different, if you add the just like different layers. So what is the formula for the composite rate of heat transfer in the composite cylinders? We will see that derivation also. Okay, so before going to that, just like we already got this formula, that rate of heat transfer formula. So we'll, for the understanding purpose, we'll solve the one numerical. Okay. So just like this is a numerical is given. A steam pipe 200 mm OD. So outside diameter is given. So is covered with 25 mm thick layer. So thick layer of insulation. So this one is the white one. This is the steam pipe. So hollow steam pipe. Inner diameter is there and outer diameter is given. That is the 200 mm. Okay. So on this cylinder, so a thick layer of insulation, insulating material is covered. Okay, with an average thermal conductivity. So thermal conductivity of that insulating material is given. Okay. Next, the temperature of the pipe surface. Pipe surface is 400. So outside surface temperature of this steam pipe, that is given. So next to outer surface of the insulation. Outer surface of the insulation also given. So this is the outer surface of the steam pipe is given. Outer surface of the insulating, so is given like this one. So this is the hollow pipe. Okay. So this is the insulating material. Okay. So outside temperature of the steam pipe, that is the T1, and outside surface of the insulating material, that is the T2. You can take like this one. Okay. Or Ti or T0, anything. Okay. So the outside surface of the insulation is equal to 50 degree centigrade. What you have to find here. So find the loss of heat from a length of just like so this is the pipe. The length of the pipe also given. So that is L. So L is equal to 10 meters. Okay. How to construct this one? So find the loss of heat. It means how to find the Q value. Okay. We already derived the formula for the Q. So here you can take the just like outside diameter uh, of the steam pipe here. So that is the inside diameter of the insulating material. We can take like this one. Outside diameter of the steam pipe is equal to inside diameter of the insulating uh, material, because on the outside of the steam pipe insulating material is placed. Okay, so you can take the inside uh, diameter of the insulating material, outside diameter of the insulating material also. Okay, so here just like then the inner radius of the insulation also given. Inner radius of the insulation means so outer diameter of the pipe. Okay, so that is the outer diameter. So DI is equal to 200 mm. So then RI is equal to 100 mm. Okay, so we can convert into meters. 0.2 so 0.1 meter, 0.01 meter. Okay, just like so we can solve this numerical like this way. So these are the given parameters. So thermal conductivity of the insulating material is given. So inner radius of the, just like insulating material, inner radius of the insulating material means outer radius of the steam pipe. So that is given. So that is the 100 mm. So that is just like 0.1 meter. So then R naught, outer radius of the insulating material. So R naught is equal to 125 mm. So convert into meters, 0.125. So that length also given, that is the 10 meters. So temperature, inside temperature of the insulating material, outside temperature of the insulating material is given. So you know the formula that according to formula, so Q is equal to 2 pi KL into T inner temperature minus outer temperature by Ln R naught by Ri, R naught by Ri. So okay, you can take directly 2 pi K value thermal conductivity is given 0.08 into length also given 10 meters. So temperatures, inner temperature is equal to 400 minus, so outer temperature is equal to 50 degrees by Ln R naught is equal to 125 mm by Ri is equal to 100 mm. So both are mm. So mm will be cancelled. Okay, no need to worry about this one. So if you solve this one, you will get the answer like this one. So in this way, just like we'll get the answer. So this one is the just like small formula, small numerical for the understanding of rate of heat transfer in the cylinders. Okay. Now we'll go for the derivation of rate of heat transfer in composite cylinders. Composite cylinders, just like so here two layers are taken. So you know that. So inside of this pipe, composite pipe, hot fluid is there. So you can take hot fluid temperature is equal to temperature of T hot fluid, and so inner fluid is there, hot fluid. So heat transfer coefficient of the hot fluid is equal to H of hot fluid. Temperature is equal to temperature hot fluid. Okay, HF. So you have to consider this one. So there are two layers, layer A and layer B. Only here we are considering two layers. Okay. Then the layer 1 temperature, just like temperature, two layers are there. So here temperature 1, it is the temperature 2, it one is the temperature 3. Okay. So this one inner hot air. This is the ambient air. So ambient air or cool air, just like we can take. So we can take this to temperature is equal to, this is the T cold fluid, temperature of the cold fluid. Similarly, heat transfer of the cold fluid, you can take like this one. Okay. So heat is transferred from here, just like a hot fluid in the just like composite cylinder. So heat is transferred from hot fluid to outside of the ambient temperature. So that is the cool fluid. See here also just like how to consider the radiuses from axis to, this is the just like coaxial cylinders. So these cylinders have the same axis. So from the center point to, this is the R1. So next to lower layer, that is the outside layer thickness, that is the R2. Next to outside uh, radius of the next B layer or B cylinder. So that is the R3. So finally R1, R2, R3 is the radiuses of the different layers. Okay, we'll see. So similarly, just like we have to consider the thermal conductivities. So thermal conductivity of the first layer, so K1, and thermal conductivity of the second layer, that is the K2. Okay, so these are the parameters, just like K1 and K2 thermal conductivities of two coaxial uh, layers. Okay, so this is the coaxial, so it means it has only one axis. Okay, so THF, so THF is the hot fluid temperature. Okay, so similarly HF, it is the H, you know, the heat transfer coefficient for the hot fluid. Similarly, TCF, it is the cold fluid temperature. So outside ambient temperature and cold fluid temperature we can take. So HCF is the heat transfer coefficient for the cold fluid. Okay. So L is the length of the cylinders, just like you can side view. So Q is the rate of heat transfer. Here we have to find out the Q value. So first of all, you have to consider here, just like you can understand that we know that heat transfer takes place from fluid to solid by convection process, then solid to solid by conduction process. So here heat transfer takes place by convection and conduction mode also. Two modes are there. So from hot fluid to inner surface of the first layer. So heat transfer takes place by convection process. Next to first layer inner surface to outer surface. So outside surface of the layer A. So heat transfer takes place by conduction process. Next to inner surface of the second layer to outer surface of the second layer. So solid to solid heat conduction. So that is the process. Next to outer surface of the second layer, B layer, to ambient temperature, again fluid. So that is the convection. So first to convection process plus conduction. So first layer in layer A plus conduction in layer B plus convection. So convection means hot fluid to inner surface of the first layer. So solid surface. So here also solid surface to outer air, that is the ambient air. So that is the cold fluid, T cold fluid. So this is the process. Now we will consider the rate of heat transfer individually. So first to convection process, it means hot fluid to inner surface of the area surface A. Next to conduction process in the surface A. Next to conduction process in surface B. Next to convection process from the surface B to ambient temperature. We will see one by one. Okay. So here just like heat transfer, first of all, heat transfer between the hot fluid and the inner surface of the first layer. So that is the by convection. You know the formula for the convections also. Here you can see first rate of heat transfer. Here you can see, you know that to heat transfer between hot fluid and inner surface. That is the by convection process. You know the formula for the convection, Q is equal to HA into temperature difference. So temperature difference. So here just like temperature difference is equal to hot fluid to inner surface temperature, that is the T1 you can take. Okay. So H is the HF. Okay. So you know that area also, because length also given, inner diameter also given. So HF area 2 pi R I L into THF minus T1. So that is the just like equation 1. From this one you can rewrite like this one, like temperature THF minus T1 is equal to Q by HF into area, like this one you can write like this one. So take this is the equation 1. Okay. Then rate of heat transfer for the layer 1, we'll see layer 1. So this is the, so you know the formula according to the just already explained the previous slides. Q is equal to 2 pi KL. So K is the just like first surface, that is the surface here. So Ka into L. So temperature between the first surface. So this is the first surface. This one is the second surface. Inner temperature T1. This is the T2. This one is the T3. Okay. So temperature difference is equal to T1 minus T2 by. So radius. So this is the inner radius. So you can take R1. This is the outer radius. So R2. So ln R2 by R1. So from which just T1 minus T2 is equal to, so Q by, so 2 pi KAL into ln R2 by R1. So this is the equation 2. So similar manner, rate of heat transfer in the layer 2. So you know that formula. So Q is equal to 2 pi KB. So second layer into L into temperature for the second layer. This is the layer B, this is the layer A. It means temperature from T2 to T3. So temperature difference is equal to T2 minus T3 by, so radiuses. So this is the up to this one R1, R2 and R3. So here R2 to R3. So it means R3 by R1. R3 by R1. So this is the formula. Okay. So from which you can write like this one, T2 minus T3 is equal to so Q into or Q by 2 pi KBL ln R2 R3 by R2. Here R2. Okay. So this is the equation 3. Okay. So you can understand like this one. Okay. So this is the rate of heat transfer in the second layer. It means so B layer. So you know the 2 pi K B into L. Temperature differences for the B. So that is T2 to T3. So T2 minus T3 by ln R3 by R2. Okay. So inner radius of the second layer, that is R2. Outer radius is equal to R3. So this is from this one, T2 minus T3 is equal to, so Q by 2 pi KBL into ln R3 by R2. So this is the equation 3. So from convection we got the equation 1. So it means heat transfer from hot fluid to inner surface of the first layer. So here just like hot fluid to inner surface. That is the equation 1. Heat conduction in layer A. So that is the equation 2. Heat conduction in layer B, that is the equation 3. Next to last equation, heat conduction or heat transfer by convection process from the outer surface of the B to cold surface, cold fluid, just like ambient uh, temperature. Okay, we'll see that one also. So the heat transfer between the outer surface to cold fluid by convection process. We'll got this one. Q is equal to, you know that HA into temperature difference. H, it means heat transfer coefficient for the cold fluid. Okay, into area 2 pi R3. R3 is the just like outside diameter of the uh, surface B. So this is the surface here. This is the surface B. Okay. So just like outside diameter is equal to R3. So up to here R2, up to here, that is the R1. You know that one. Okay, from this equation, T3 minus TCF is equal to Q by HCF into 2 pi R3 into L. So this is the equation 4. So finally you got the 4 equations. Okay, so equation 1 we got that, that is the, so T HF hot fluid minus T1, that is the first equation we got, Q by HF into area 2 pi R1 into L. So that is the equation 1 we got. This is equation 1. Sorry. So similarly, in second equation we got that one in the previous slide already. So T1 minus T2 is equal to Q by, what is that one? Q by 2 pi KL by ln R2 by R1. 2 pi K A into L by ln R2 by R1. So this is the equation 2 we got. Similarly, T3 minus T2. So that is the, we got the equation Q by 2 pi KB, thermal conductivity of the layer B into L by ln R3 by R2. So this is the equation 3. Okay. So already we got the equation 4 here also. That one. This is the equation 4. It means so that is the just like T3 minus TCF is equal to Q by HCF into 2 pi R3L. Okay. So this is the equation 4. So add the equations 1, 2, 3, 4. Okay. So 4 equations how to add. So we have to add the left side terms and the right side terms. If you add the left side terms, that is the temperatures. First one is the just like THF minus T1 plus T1 minus T2 plus T2 minus T3 minus, no, this is T2 minus T3, T2 minus T3, so plus T3 minus TCF. So this is the left hand side. Okay. So from which minus T1 plus T1 will be cancelled, minus T2 and the plus T2 will be cancelled, and the minus T3 and the plus T3 will be cancelled. So finally you got the initial temperature, that is the hot fluid temperature minus cool fluid temperature. That is the left side term. So similarly, if you add the right side terms, just like Q by HF 2 pi R1L, Q by 2 pi KA into L into ln R2 by R1, R2 by R1, R2 by R1. Similarly, so equation 3, Q by 2 pi KBL by ln R3 by R2. So similarly, Q by HCA plus 2 pi R3 into L. If you add this, so these terms, okay, we will get the formula. So like this one, just already noted in the PPT. So you got the final formula. So this is the left side of temperatures. You know that initial temperature, final temperature. It means temperature of hot fluid minus temperature of the cold fluid. In right side terms, in all the four terms, just like q by 2 pi L is the common term. If you take that common term, that from the first equation, 1 by HF R1 plus 1 by Ka ln R2 by R1, 1 by Kb ln R3 by R2, and 1 by SCF R3. So this is the formula for the just like so rate of heat transfer in the composite cylinders. So finally, so Q is equal to Q. What is the Q? Rate of heat transfer in the composite cylinders. That is the final formula is equal to 2 pi L into, so initial temperature minus final temperature. Initial temperature is the hot fluid temperature. Final temperature is the cold fluid temperature. Then 1 by just like, so convection process, conduction process, convection process. It means heat transfer from hot fluid to inner surface. So heat transfer in the first cylinder, heat transfer in the second cylinder. Here heat transfer from the outside surface of the cylinder to just like cold fluid. So we'll get this one. So just you can write like this one also. Thermal resistivity formulas. Okay, you can write like this one. So Q is equal to temperature differences THF minus TCF divided by, so RA plus R1 plus R2 plus RB thermal resistivity. You know that. So temperature, so this is the thermal resistivity. It means so RA. So here hot fluid to inner surface. Next to thermal resistivity RA. Similarly, thermal resistivity RB, thermal resistivity so RB. You can take like this one. RA is the thermal resistivity of the layer A, layer B. Otherwise, you can write like this one. This is the R1, R2. Okay. So what is R1? You got that one. What is the R1 and the R2? Thermal resistivity is already just we have already shown here. So this is the RA. This is the R1. This one is the R2. This one is the R3. Okay, thermal resistivity. So it occurs by convection process, it occurs by conduction process, it occurs by conduction process, and it occurs by the convection process. So in this way, just like if there are two layers, you can write like this. If there is three layers, you have to add this one, just like with the third layer. So here you have to add like 1 by Kc by Ln R4 by R3. Okay, if the one more layer is there, just like we have to add 1 by just like Kd Ln R5 by R4. So this is the formula. So in this way, just like you can solve the rate of heat transfer in different number of composite cylinders. So got this is the final formula. So final formula is equal to, so inlet temperature minus outlet temperature by sigma R thermal resistivity. Okay, so thermal resistivity, what is thermal resistivity? Resistivity is already have shown in the previous slides also. We can refer that one. Okay, now so by using this formula, so you solve a few more numericals. So for the better understanding. Okay, so this is the just like if there are number of concentric cylinders, just like we can write the general formula like this one. So that is the 2 pi L into initial temperature minus final temperature. So initial resistance for the convection process, this is the final resistance, thermal resistance for the cold fluid. So it means THF plus R1. Here TCF into Rn plus 1. Here you can see there are two layers. N is equal to two layers. It means you will get Rn plus 1. It means so one more radius you will get. Okay. Plus Ln Rn plus 1 by Rn by Kn. So that is the formula. Okay. So if it is N is equal to two layers. Here just like we will get first this one and the second this one. Okay, so in this way just we'll get the different uh, rate of heat transfer in the different layers, number of layers is given. So this is the final formula. You have to remember this one. So by using this one, just like we solve small numerical. So okay, so first of all you will see the water enters a pipe at a temperature of 60 degrees. Okay, so water enters a pipe at a temperature of 60 degrees. So there is a pipe. So in this pipe water is flowing. Temperature of the water is equal to 60 degrees. Assume the pipe is made of stainless steel. So that is pipe is made by stainless steel. Thermal conductivity of the pipe also given. And that pipe has an inner and outer diameters. So the pipe. So this is just like pipe. Like this one just so in the hollow space water will flow. So water is flowing. So this is the inner axis, inner radius r1, outer radius r2. You can take like this one. So inner and outer diameters are given, convert into just like radiuses. What is the outer temperature of the pipe if the heat lost at rate of 15 kilojoule per meter centigrade? So here Q is given. Q is given. So temperature, this is the inner temperature. Outer temperature is the T2. You have to find that one. Okay. So assume temperature is constant down the length of the pipe. So that is the numerical. Now we'll solve that numerical just. So first of all, we have to write the data what was given in this numerical. Okay. So this is just like just I'm giving the direct formula. Q is equal to 2 pi KL into Ti minus T naught. Here just like we are considering only the conduction process in the stainless steel pipe. Okay, not convection, because here heat transfer rates are not given. So only conduction, thermal conductivity. So stainless steel conductivity is given. K is equal to 30 watt per meter Kelvin. Okay. So this is the inner diameter Ri, outer diameter, outer radius R naught. So Ri is equal to 10, R naught is equal to just like 12.5 centimeters, convert into meters. Okay. So outer temperature you have to find out. Inner temperature is 60 degrees. So Ti is given. So Ti is equal to 60 degrees. So T naught you have to find out. Say here T naught you have to find out. So Q also given. So 1500 kilojoule per meter second. So that is on just like kilowatts. So I have to convert into 15,000 watts. So into 2 pi, you know that K is the thermal conductivity. Here thermal conductivity also given. And length, that is the unit length is taken. So length is, we can take, that is 1. And temperature Ti is given, that is the 60 degrees centigrade. Minus T naught you have to find out. Ln R2 by R1. So D2 by D1. So diameter, outer diameter by inner diameter you can take. Outer radius by inner radius. Anything you can take. So from this, if you solve this one, you will get the T naught value. So T naught is equal to 42.2 degrees centigrade. Okay. So in this way, just like we'll see, this is the just numerical which is related to conduction process only. Now we'll see the composite related numerical. Then we'll stop this one. Okay, a steel tube, so that is the K is equal to 43.26. Steel tube thermal conductivity is given, and steel tube inner diameter that is given, that is a 5.08 centimeter. So and 7.62, that is the outer diameter. Okay, so there is a steel tube, so the steel tube is covered with the one insulating material. So insulating material thickness also given, that is a 2.5 centimeter layer. Okay, thermal conductivity of the insulating material also given. Okay, so okay, outside surface of the tube receives the heat from the hot gas. No, inside surface of the tube receives heat from the hot gas. Here, just like heat is transferred from the hot gas to inside surface of the steel tube. So here we have to consider the convection principle. Okay. So for that one, just like a hot fluid temperature also given 316 degrees centigrade, and heat transfer coefficient also given, that is 28 watt per meter square Kelvin. Well, the outside surface exposed to the ambient temperature, same. So outside surface is the ambient temperature, atmospheric condition. So that is the temperature, outlet temperature, final temperature also given. So heat transfer coefficient of the, just like cold fluid, uh, heat transfer coefficient of cold fluid. So that is the 17 degrees watt per meter square Kelvin. Hot fluid, heat transfer coefficient of hot fluid. So that is also given. That is the how much? So heat transfer, that 28 watt per meter square Kelvin. So all the parameters are given. Just we have to calculate the heat loss. Q value how to find out. Length also given. L is equal to given. L is equal to 3 meters are given. So first of all, we have to note the all the data. So which is given in the numerical. So here just like steel tube thermal conductivity K1 is given. Okay. So that is the 43.26 watt per meter Kelvin. So inside diameter of the steel pipe, steel tube. Okay, so that is the D1. That is the 5.06 centimeter converted to meter. Then so we can take just we can find out the radius also. Radius, inner radius. That is the R1 or RA you can take. Then R1 is equal to 0.025 per meter. Next, outer radius of the steel. Okay, that is the just like this is R1, this is the R2 you can take. Okay, for the understanding purpose. Hollow steel tube. Okay, so in the hollow space hard fluid is there here. So it is one insulating material is layered on this pipe. Okay, this is the insulating material. So inner radius, that is R1, this is the R2 outer radius. So next to R3, it means outer radius of the insulating material. So that is R3. So R3 also here. R3 means R2 plus thickness of the insulating material. How to consider this one? Then R2 is equal, R3 is equal to R2 plus outside diameter, outside radius of the steel pipe plus thickness of the insulation radius, insulating materials. Then R3 is equal to this one. So 0.0631. Finally, you got R1, you know that, R2, you know that, R3 also, you know that. Okay. Next to HF, you know that, HCF also, you know that. Okay. So inner temperature THI is given. That is the how much? The temperature is also given. So 316 degrees centigrade, and hot fluid temperature TCF. So that is the 30 degree centigrade. So all the parameters are given, just like you can use the formula and you can solve it. So this is the given formulas. Okay. Thermal conductivity of the insulating material is given. Thermal conductivity of the steel pipe. So that one also given. Okay. Hot fluid temperature TA. So convert into kelvins, and ambient temperature also we can convert into kelvins. So okay, heat transfer coefficients HA. So HA is I write here, or you can write like HF, hot fluid, HCF. So that is the 28. So this one is the 70. Okay, so you can take the formula directly. So that is the inner temperature. So that is the T1. TA means TH hot fluid minus TC cold fluid. You can write like this, or you can write TA also. TA is the inner hot fluid temperature. TB is the outer cold fluid temperature. So you know the formula, just what was derived in the previous slides. So 1 by 2 pi R1L into HF. Okay. So 2 pi ln R2 by R1 by, so 2 pi K1L. Similarly, ln R3 by R2 by 2 pi K2L. So, and plus 1 by 2 pi R3L into HCF. Okay. So if you know all the values are given data. So if you substitute the values, and we will get the rate of heat transfer in the composite cylinder. Just like this is the hot fluid temperature in kelvins. Otherwise, just like here 273 is adding, here 273 is subtracting. So no need of conversion of K also. Directly you can write like this one, 316 minus 30. Okay. So here just like 1 by 2 pi R1 is already, you know that length also given, and hot fluid heat transfer coefficient of hot fluid 28 also given. So in this way, just like we can solve what are the numericals which are related to composite cylinders, we can solve this numericals. So thank you for watching this class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.